Okay, we are a few people today, but I was expecting that. However, the thing that I will be discussing today is a relatively important topic for compression and for transformations in general. So we were discussing the transform coding, but probably the most important thing to mention about this topic is the optimality of a transform. How do we measure the optimality, and how can we design an optimal transform? However, the design of an optimal transform will depend on statistics that we obtain from the signal. Therefore, it will be signal dependent in a sense, and it's going to be named like this. But first, let me write the topic. It's the Carhonen-Loewe transform, abbreviated as KLT, which is the optimal transform. Of course, it's not the optimal transform for any given signal, because the optimal transform for a given signal is maybe its principal components or the signal itself, which can be considered as a basis signal when normalized, and all the other signals that you can think of can be designed orthogonal to that using Gram-Schmidt orthogonalization or something like this. So there will be only one thing to represent it, but we are talking about random signals here. So for random signals, you need statistics that can be gathered from a lot of data, or you may be given the statistics of that random signal. Random signal is a signal which you don't really have. So for those, what is an optimal transform? That is the significant question that we have to answer now. And we will do it like this. We will say that a signal X, let's assume, can be represented by a linear combination of some basis vectors U1 up to UN, okay, like this, Y2, U2 plus dot dot plus YM, UM. I'm putting these Y1, Y2, YM, etc. They are, of course, the scales, which defines the transformation from the values of X, which are like this, X1, X2, all the way up to Xn. Okay, so from X1, X2 up to Xn, I am transforming them to Y1, Y2, all the way up to Yn, and Ym is an intermediate place to indicate some in-between points. I will explain why we are doing this. Then Ym plus 1, Um plus 1, plus all the way up to Yn, Un. So it's an n-dimensional data vector, this X vector, and we are transforming it to another n-dimensional vector consisting of Y values, that kind of a transformation. It is defined by its basis, okay? This basis, if they are orthonormal basis, these U's are orthonormal, then every one of these Y1, Y2, etc. can be obtained by, for example, taking the inner product of X with U1 will give you Y1. Taking the inner product of X with U2 will give you Y2, etc. Therefore, that inner product will define our transformation. We can write it like this. So Yi is essentially X inner product with Ui. If UIs are orthonormal, and we will assume that they are orthogonal. They are orthonormal. So we will be designing an orthonormal and optimal transform, not any transform, but orthonormal. And here we know that this kind of an inner product is defined to be summation, let's say, k from 1 to n x sub k times ui's kth value. But sorry, it's not a vector, it's a value conjugate. Because in the inner product, the general formulation is to use the conjugate of the second term. This is in the form of a summation like this, because these two are straightforward finite length vectors. If they are continuous time functions, then the first signal will be multiplied by the conjugate of the second signal, and they will be integrated instead of summing up. But yeah, there we go. And from here, we see that this kind of a summation essentially makes the y vector to be constructed in general using a vector I'm gonna call as v times x vector, where v is a matrix, and the v matrix is constructed as the conjugate of u vector. Let me write it like this: u conjugate, and where u is, I will write it here, u vector is consisting of u1, u2, etc., all the way up to un. So these are the basis vectors that we have here and here and here. I'm putting commas in between, but actually they are column vectors. So every column vector, I can also write it like this if it's more convenient to use. There's a u1 vector. These are vectors actually. Spans the first column, and then the u2 vector spans the second column, and then it goes on like this. So this makes, by stacking the u columns, you construct a u matrix, and when you conjugate it like this, you come up with a v matrix. So y is equal to v times x. You can write it like this. Or if things get complicated like this, you can also write it like, so y vector is u conjugate times x. And we know that for orthonormal set of basis vectors, this u conjugate is also equal to u inverse. All right. Okay, so that's what you are gonna do then. You will find the basis. You will find these basis vectors, design those basis vectors, and stack them up and take the inverse of that stacked matrix and call it the transform matrix, which is here. So this is our transform matrix. That's how we construct our transform matrix. Now let's come back to our design. What I'm saying is designing the transform matrix is equivalent to designing the basis vectors. We will be designing the basis vectors for designing the optimal transform. So what is a best set of these basis vectors? The strategy that we will proceed is to crop off this summation from a point, from an M point, so that to the left, I will take as an approximation, and to the left of it, whatever is left will be the error, right? If I crop from someplace, this is what we have. As a matter of fact, if we take a look at our previous example that we see in the last hour, it was like this. We had this signal consisting of a summation of orthonormal basis vectors. These basis vectors are here in the form of matrix, but they are orthonormal. And in this new representation, the coefficients are 22, -2, 0, and -4. And the amount of error that we make if we crop from here, for instance, and eliminate these last two items is just the summation of these two terms and their corresponding magnitude, which would be corresponding to 0 square plus -4 square, which will be 16. So if I crop from here and take these two as our approximation, 16 square of this would be my error. And that's what we really have in this particular example. So that gives us an idea here. If you really want to minimize this error by cropping from some place, essentially what you are trying to do is you are trying to minimize these coefficients, the coefficients of the error term, like ym plus 2, ym plus 3, ym plus 4, etc., all the way up to yn. All of these coefficients, if they are small coefficients, then my approximation will be good and my error will be low. So that is our optimality criterion, which let's try to minimize. First of all, the error term is a vector in the form of x minus, I will say x tilde, but I didn't mention about what x tilde is. X tilde is this approximation. So the approximation will be notated as x tilde. And we want this error term, x minus x tilde, to be as small as possible. And this is the remainder term from n plus 1 to n yj uj. Okay, so this is our error term. But it's a vector, it's in the form of a vector, and it's not feasible to minimize a vector. So let's convert it into a term of scalar like this. Let's say E, which is the error term that we want to minimize, as the expected value of norm square of this error term, epsilon. So it's equal to essentially the square difference between x and x tilde. So this is E, and we want to minimize it. How do we minimize it? There are ways to do that, but the easiest from calculus or from mathematics in general is to take the derivative with respect to our fine-tuning variable or tuning variable and equate to 0. We take the derivative and equate to 0. But taking the derivative will be a little bit tricky, of course, in this case. By the way, this E will also be equal to the expected value of summation from n plus 1 to n yj uj. This was the error, right? Norm square. I can also write it like this. And this norm square is essentially achievable since, or maybe I can write it here. It's also like the expected value of the error transpose times the error, right? This is equal to this, right? And I wrote this term in this format. I could also write it in this format here, and I'm gonna do it right now. It's the expected value of summation from n plus 1 to n yj uj transpose, because this is epsilon transpose that I'm writing, times summation from n plus 1 to n yj uj. Okay, this is how we write epsilon transpose times epsilon, error transpose times error. So it's an interesting summation, multiplication of two summation terms inside the expected value. So how do we multiply two summation terms? We multiply one by one, right? For instance, ym plus 1 um plus 1 transpose times ym plus 1 um plus 1 is the first term. Then the first with the second of the second transformation, then the first with the third, the first with the fourth, etc. And then the second with the first, second with the second, second with the third, and then third with the first, third with the second, third with the third, third with the fourth, etc. It goes on like that. So there are many terms here. But notice one thing here, these terms are mostly zeros, especially the terms that correspond to different indexes, like the first with the third, for example. The first one will be ym plus 1 um plus 1 transpose, and the third one from the second summation will be ym plus 3 um plus 3. And when you multiply um plus 1 transpose, let me write it in blue here, um plus 1 transpose times m plus 3, for example, this is equal to 0. Why? Because these are basis signals. UJs are basis signals, and basis signals are orthogonal to each other. They are non-orthogonal only to themselves. So all of the cross terms in this multiplication of two summations, all the cross terms will be zeros. They will correspond to different UJ transpose and different UK. So I can essentially write it like this in red this time. UJ transpose times UK is actually equal to 0 whenever J is different than K. And this multiplication, however, becomes 1 when J is equal to K. So if J and K are the same, not the cross terms, but the term with the same index, then this multiplication becomes 1. That is orthonormal behavior, right? So by this observation and by closely inspecting then what is going on in here, we will notice that this term will multiply with this term only when this J is exactly the same as this running index J. And then the multiplication will be Yj times Yj times 1, because Uj transpose Uj will become 1. So it will be Yj times Yj, which is Yj squared. And it will be available to us for all J from n plus 1 to n. That's it. Like this. Yj squared times 1. It will be throughout a single summation only. Normally, if you multiply two summation terms, the result will have to be handled in the form of a double summation, but the cross terms in this double summation will cancel out to become 0 because of orthogonality, and we will only have a single summation term whenever j is equal to k, in other words. So j and k simultaneously run from n+1 to n, and it's yj times yk when k is equal to j, which means it is yj squared. So this is the error term that we have in the form of a summation. Now I will continue again in blue, because from here, first I will continue and put this in a different form. That different form is the summation first, and then the expectation goes inside. Because summation and expectation can interchange their places because they are both linear operators. Expectation also has the integral or summation operator inside, so they are both linear operators. Their orders can be interchanged. Expectation yj square. Okay, so these two top and bottom terms are the same. And from now, I will proceed with blue, because there is one term that I have to elaborate. Then the summation from n+1 to n will be handled later. So this is the term first I want to obtain. What is it? How can I express this? Yj squared, one term inside this summation. And that term is expected value of yj transpose times yj. Excuse me, we don't have a we don't have these underscore bars. These are not vectors. But I'm still writing it in the form of a transposition because it is actually yj times yj. Okay, this, don't get confused with this transposition. Or if you're not comfortable with it, you can perfectly eliminate it. Yj times yj. Let's think of it like this. And then from here we can continue. First, I will write yj in one form like this. Uj transpose times x. And then I will write yj, the second yj, like x transpose times uj. The reason that I am writing two yj's in a different manner is because it doesn't really matter. For real uj, uj transpose x corresponds to the inner product of x and uj, and x transpose uj will also correspond to the inner product of x and uj. So the inner product of x and uj here or here will all give you yj, like this or like this. These are two alternative ways of writing the same yj. But if you write it like this, some magic will happen. And that magic is deliberately designed, of course, because the first yj I wrote uj to be at the left-hand side. And the second time I'm writing this second yj, I write it like this so that its uj is left at the right-hand side of the right form of the expression. Because when I write it like this, it means that the random vectors, which are x, of course, the random signal, can be left inside at the inside part, and the exterior parts are uj transpose and uj, which can be taken out of the expectation operator. That's because they are not random. So expected value of a times x is equal to a times, a can be taken out of the expectation, a times expected value of x, in other words. So the left hand u can be taken out of the expectation operator like this. Then inside the expectation, it begins like x times x transpose. And then the right-hand side of uj can also be taken out of the expectation operator from the right-hand side, like this. Now, when you closely inspect what this is, it's like containing all the cross terms of the value of x. X is a column vector. X transpose is a row vector. If you multiply a column and a row vector, it will give you an n by n matrix, right? And that n by n matrices expected value will give you automatically, for example, in the diagonal, the expected value of x1 times x1 and expected value of x2 times x2, which are just zero lag expectations. But in the off diagonals, it will be like the expected value of x1 times x2, expected value of x1 times x3, etc., etc., which is the definition of the autocorrelation, by the way, matrix, as we all know from other concepts as well. We are very comfortable with this autocorrelation definition. So this expectation in the middle is the autocorrelation. We know it. So that's it. It's uj transpose rx uj, one of these expectation operators. Now I can replace this expectation operator with this expectation expression, with this new expression into here. And then I can write it like this. That is equal to expected, no, first there's a summation, of course. Summation j from n plus 1 to n. And inside it, I will write uj transpose rx times uj. Yeah. And it looks pretty nice. So this is the thing, it's the error that we want to minimize. With respect to what? Of course, you have to be careful about what's your minimization or optimization parameter that you are gauging. And that is uj or uj transpose, whatever. The basis vectors are the things that we are designing. So we will minimize this with respect to uj. And its minimum will occur when, for example, you choose uj to be equal to 0. Since there is uj transpose and there is a symmetric autocorrelation matrix, the tuplets matrix in between, and this one here, uj transpose uj is like uj square. So you cannot have anything negative from here. These terms are always positive. Let me maybe also write it. These are always positive. They can't be negative. And the only way to minimize this summation is then to make uj's to be equal to 0. Okay, that will give you a trivial solution, but it will not give you a solution essentially, because if you say that uj is a 0 vector, then it can't be a basis vector. Basis vectors have unit norm. So we found a solution by taking the derivative of this expression with respect to uj and equating to 0. Will give you uj is equal to 0 vector, but it's a wrong solution. So there is something wrong here. We made a mistake about what to minimize. And the mistake that we made is to ignore the constraint. The constraint is, so we have to take the derivative with respect to uj of this term, take the derivative of this term with respect to uj and equate to 0 with the condition that, or subject to, the fact that uj norm must be equal to 1 for all j values ranging from m plus 1 to n. But the solution, the selection of this m is arbitrary. You can even start from the first or the second or the third or 100, 1 millionth, etc. We don't know where to crop from yet. It's just an endpoint. So it's safe to assume that this condition is valid for all j from 1 to n. And this derivative, similarly for all uj from j from 1 to n, this derivative is supposed to give you 0. But this is a constraint. I didn't incorporate this constraint yet. So the conditional optimality is of concern here. It's not only an optimum point corresponding to its derivative is equal to 0, but with a condition, we have this optimality constraint. So how do we take conditional optimalities? How can we incorporate this subject to norm of uj is equal to 1 condition? And the way to do it, by the way, I can write like this: the square norm is equal to 1, which will be written as uj transpose times uj is equal to 1. The incorporation is done by the so-called Lagrange multiplier technique, which is a technique that you are supposed to know in calculus courses in the first year of undergraduate. In calculus, this thing is shown, the conditional derivative using Lagrange multipliers. So instead of e, I will devise a new term. Let's call it e prime. But this prime does not mean a derivative or anything. It's just a new error term that incorporates both the expression to be minimized like this, uj transpose rx uj, and within a Lagrange multiplier, it also within the same summation, or I could also put a parenthesis here and then close it over there. Maybe I should do that. Yeah. Why am I just repeating this summation term here? Let me open a parenthesis from here and put a term like lambda times, but it's lambda j because it depends on which j index we are at, 1 minus uj transpose uj. Why? What does that mean? This condition is a condition which must approach to a value of 1. But I didn't write uj transpose uj minus 1 because normally from the derivative of this part, it already tries to make uj's to be 0 when I equate the derivative to be equal to 0. So this is already trying to reduce the values of uj, but this term will help me to keep uj transpose times uj to be as close to 1 as possible. Actually, it will make it to be equal to 1. With this Lagrange multiplier, that must be positively selected. So lambda j's are also positive. So this is the new error term, which I want to minimize. Therefore, I will take the derivative of this one with respect to all of the uj's, j ranging from m plus 1 to n. So this is equal to 0. This derivative is equal to 0. So now I have to take the derivative of the term. It looks a tad complicated, and it is indeed complicated. uj transpose rx, by the way, we have rx matrix here, of course, and uj, and its derivative with respect to uj, what is it? And then we have this term, and we will take the derivative with respect to uj again. Interestingly, it's not that difficult. The result is not that difficult. It's from vector calculus. I will only indicate the answer. I will give you the result, but the reasoning or the idea can be explained as follows. There is uj here and uj here, so it's like uj square. And what is the derivative of uj square with respect to uj? It is 2uj, all right? So when you take the derivative, what you will have is actually something like this: 2rx uj. Rx is like a coefficient over there. So it's like a times uj square. What's the derivative of a times uj square with respect to uj? It is 2 times a times uj. So 2 times rx times uj. Of course, it's not as easy as this one because these are vectors and matrices. But it just happens to be the same result. And where did the summation go? The summation went away because we are taking the derivative for a particular j, and for that particular j only, we have this derivative. The all other terms just vanish because they are not uj anymore, they are uk, and the derivative of uk with respect to uj is 0. So we don't have a summation, we have only the jth term here in this expression. So the derivative of this with respect to uj is this. And for the right-hand side, what is the derivative of this with respect to uj? There is lambda j times 1, which is just constant, and the constant's derivative with respect to uj is 0. But there is a minus lambda j times uj transpose uj. It's like minus lambda j times uj square. And what is the derivative of minus lambda j uj square with respect to uj? It is minus 2 lambda j uj. Okay. Again, an easy result is achieved. And this is equal to, this expression is equal to 0. The 2's can be cancelled because you can divide both sides of the equation, 0 and this by 2. And eventually you will get Rx times uj minus lambda j uj is equal to 0. And essentially, it makes a 0 vector for our case. And it gives us Rx uj is equal to lambda j uj. Let's put this in a red box because it didn't give us the result, but it almost gave us the result. So what is uj from this equation? It looks interesting because both sides of the equation has uj's. So am I gonna, like, cancel uj's from both sides of the equation and say Rx equals lambda j? Well, that's all absurd, of course, because one of them is a matrix, the other one is a scalar. So what is uj from this kind of an equation? Does any of you guys have any idea from here? What is uj? How can we solve for uj? Can you remember? Does it inspire or trigger any result in your mind? I'm asking you guys.
I think it's like ones.
One vector consisting of 1, 1, 1, etc.
Yes.
I would say why? What makes you think that uj can be replaced with a one vector?
Yeah, because Rx uj equals lambda j uj.
Um, for some particular case, it may be an answer, but in general, we cannot really say that. And actually, one is just a single answer, but for different j's, this is supposed to give you different results because every uj is different from another uj. So it can't be a generic answer. It's maybe a specific or one answer maybe in some certain cases. By the way, it cannot be all ones. It must be normalized to 1 because it must be unit norm. So you divide it by the norm, you may say. But the answer is not like that. For that, again, you must go back several years in your undergraduate courses to the linear algebra course, where we were dealing with equations like a times x is equal to lambda times x. So what is x? It's the same equation, by the way. But we were given the answer in linear algebra in a different way. It was actually called an Eigen Decomposition. So x is actually the eigenvector of A, and lambda is the eigenvalue. It is an eigenvalue of A. That's what you really need to remember, but it's difficult to remember. I would appreciate that. That's why I asked you first. Maybe you could remember. So looking back to this equation, we see that essentially uj is then an eigenvector of Rx with a corresponding eigenvalue of lambda j. So that's what it is. Let's write it down. Uj is an eigenvector of Rx matrix. So the autocorrelation matrices eigenvector is Uj. That's nice. Because that's what we were looking for. What is Uj? What are Ujs? They are eigenvectors of Rx. If they are not normalized, you may want to just divide the eigenvector by the norm of the eigenvector, and it will be normalized. The fascinating thing is that these eigenvectors automatically will become orthogonal to one another. So one eigenvector of this triplet matrix Rx is orthogonal to another eigenvector of Rx. They are orthogonal. And that's a property that comes from the triplets behavior of this autocorrelation matrix Rx. This is valid only for Rx. You cannot say that if I put any matrix here, their eigenvectors are orthogonal. No, they are not, of course. They're of course not. But for autocorrelation matrices, they are. And what are these lambda j's? Well, those lambda j's become relatively important still, although they are not the ones that we're looking for. We are looking for UJs. The problem is we don't know where to put the first UJ as U1 and the second UJ as U2. We don't know which is which. Because when you ask MATLAB, for example, to show you the eigenvectors of an autocorrelation matrix, they will show you the eigenvectors. But which one is U1? Which one is U2? Which one is UN, the last one? You don't know. That also requires some design, further design. And that further design is the last step of the so-called construction of the Cardinal-Level transform, or KLT. And for that, we will continue with further equations like this Eigen equation is one of them. And so let me write the error term once again. It's not the error term E prime, but the error term, this one, and not the constraint one, the one that we are really trying to minimize. And that was, if you may remember, J from m+1 to n Uj transpose Rx times Uj, right? This was our error. Now I will take a look at this part and see that Rx times Uj here is equal to lambda j times Uj as the answer. So let me write it like that. uj transpose times lambda j times uj. And here lambda j is just a scalar that can be taken from in between these two vectors to here. So it makes lambda j times uj transpose times uj. And uj transpose uj is 1 because they are orthonormal. So this will be simply the summation from n plus 1 to n lambda j. So the error is summation of lambda j from n plus 1, j from n plus 1 to n. So how can I minimize it? So this is the thing that we want to minimize. How do we do that? We do it by judiciously or deliberately selecting the last lambda j's to be small. These lambda j's, if these lambda j's you choose to be small, and by the way, these lambda j's are always positive because of the tuplets nature of this autocorrelation matrix, and their eigenvalues are therefore always positive, greater than or equal to 0. So you choose the lambda j's that are the smaller ones to be at position n plus 1 to n. So the last lambda j's, you want them to be the smallest or the smaller lambda j's. And all the j values from 1 to m, you keep large, so that this thing is, which is the error, is minimized. So what we really do is we choose lambda j's on the j-axis to be like in a descending order. Sorry for my messy drawing. So this is the layout of the eigenvalues that I put on the j-axis in a descending order, so that if you choose any m value to the right of it, the summation will be minimum. And the approximation is to the left-hand side. Approximation is to the left-hand side, and they are large. So the approximation is rich. It's a good approximation. And the right-hand side is just the error term, which will give you the minimum error. So this shows us the way to sort the eigenvalues. But every eigenvalue is attached to an eigenvector. They come in pairs. Like there is a lambda j and there is a uj, which is the eigenvector, an eigenvalue and an eigenvector. They are in the form of pairs. So sort these pairs according to lambda j, the eigenvalues, then it means you are also sorting according to the eigenvectors. So, or let me put it this way, you are automatically sorting the eigenvectors too, when you sort them according to their eigenvalues. And when you do that, it will give you the U matrix, which is consisting of U1 vector, which corresponds to the largest eigenvalue. And then the U2 vector, which corresponds to the second largest eigenvalue, but the one which is less than the first eigenvalue. Then U3, which is the third largest eigenvalue. And it goes on like this until Un, which will give you the smallest eigenvalue, which will correspond to the smallest eigenvalue. So this will be your U matrix, the rendition of the basis, and the transform will be U inverse. As simple as that. So this will be equal to the Carhon and Loewe transform that you will get. which rolls back to our original question. So how do we obtain an optimization? We obtain an optimal transform, statistically optimal transform, if we know the autocorrelation. Of course, the knowledge of Rx is critical here. If you don't have the autocorrelation, or if you cannot approximate the autocorrelation, you cannot design your optimal transform. You need to have the autocorrelation. And these eigenvalues, lambda j's, will automatically define how much error on the average, or how much expected error you will be having when you cut from a place and chop off all the rest, replace them with zeros. That's what we did our very first example. But we had to calculate one by one how much error we made. You don't have to really calculate. If you just sum up these eigenvalues here, sum up j from n plus 1 to n, lambda j, this is the error that you will get. So the eigenvalues will also give you how much error you are making. So if you have, for example, an 8x8 autocorrelation matrix, and you want to find the 8x8 transform, you find the eigenvalues of this 8x8 autocorrelation matrix. And if some of these autocorrelation, if some of these eigenvalues of the autocorrelation matrix are like 0, literally 0, then it would be very nice. Or if their eigenvalues are very small, it would be very nice. It means that you can put them at the last position in the row, and you can just eliminate them. Without the knowledge of those, you will still have perfect reconstruction. It would be something like this. Let me roll back to our very first example, which was here. So technically speaking, if you find the Cardinal-Loewe transform, it will give you probably these eigenvectors, but their ordering will be different. The first one will be this, the second one will probably be this, the third one will be this, and the last one will be this. So the shuffling of these eigenvectors will be a little bit different. And it also clearly shows that when you eliminate the last one, you will have just 0 error. And if you eliminate the last one and the one before that, the error will be 0 times the square of -2, which is 4. So it tells me that the eigenvalues are 0 square, -2 square, which is 4, -4 square, which is 16, and I don't know what the square of this one is, but it's just the square of that. So these were the eigenvalues. When you sort those eigenvalues, you will find the optimal transform. So the question that I have now for you is, if I give you a set of signals, or if I give you an image that could also be in the form of an image, because it's always possible to find the autocorrelation matrix in 1 dimension. This is 1-dimensional, by the way. It's not a 2-dimensional image transform. But for applying to images, you just apply it to the rows and the columns. We know how to do that. So will you be able to find the Cardinal-Loewe transform if I give you a set of signals? Because that's what I did in the previous first midterm. I gave you, or I wanted you to first construct your signal, and from that signal, obtain the autocorrelation matrix I asked you, or the autocorrelation. Many of you guys did it, but then afterwards I put on the Mergen Canvas page an easier way to find the autocorrelation matrix. Please look at that function. Please find the function and take a look at it. And so you have to find the autocorrelation of the signal. If it's an example signal, you can use time series. You can record them and then make estimations. Or if the signal is already given in terms of the statistics, then it means the autocorrelation is there. And once you have the autocorrelation, you should be able to find the eigenvalues and the eigenvectors. And the question is, will you be able to do that? And the answer will be a clearly yes. And the question that I will ask you is in the final take-home examination will be the continuation of this example, where it will be a 2-by-2 case. The autocorrelation of 2-by-2 will be R0, R1, R1, R0. Okay. And R0 is, and let's assume that it's equal to the covariance, which means it is zero. Okay, that's usually a good assumption. And if it's not zero mean, then you can just subtract the mean from the signal, and it becomes zero mean. And the covariance diagonal elements are the variances, because I'm also assuming that these are stationary signals. So the R0, which corresponds to x1 times x1's expected value, and the R0 here and here, which is the expected value of x2 times x2. From x1 to x2, it doesn't change statistics, it's stationary. So these two will both give you sigma x squared. And the off diagonals will give you rho times sigma x squared. And rho, we already know from our discussions of predictive filtering, is the correlation coefficient, which is something between -1 and 1. It can't be larger than 1. And that makes sigma x squared in parentheses 1 rho and rho 1. So what are the eigenvalues and eigenvectors of this one? Although I will also ask it again in the form of a take-home examination. In the take-home exam, I will ask you to compare it with some other optimization techniques that I will explain within the question. But one optimization is already done here. Okay, all along we did the optimization, which tells us that this is for the KLT, for the optimal transform, you need to find the eigenvalues and the eigenvectors. And the eigenvalues will be, for this one, R0 plus R1 will be one eigenvalue, and R0 minus R1 will be the other eigenvalue. If R1 is positive, if the two neighboring coefficients are positively related, then lambda 1 will be the larger one and lambda 2 will be the smaller one. And the corresponding eigenvectors are U1 will be equal to alpha and alpha, and U2 will be equal to beta and minus beta. I'm not giving specific numbers, numericals for this alpha and beta here, because they are just arbitrary. So we need to normalize them. U1 and U2 must have unit norm. And when you normalize them, this becomes in 1 over square root of 2 parentheses 1, 1. And U2 becomes in 1 over square root of 2 parentheses 1 minus 1. So these are the eigenvectors corresponding to the eigenvalues like this. And it doesn't really depend on what you say as R0 and R1, as long as R1 is positive. If R1 is negative, by the way, then lambda 1 will be the smaller one, and lambda 2 will be the larger one. So the the positions of U1 and U2 will have to be interchanged. It will be, excuse me, it will be 1 minus 1, and then the second one will be 1, 1. But the structure will be the same. So this U1 and U2 is something which will give you a U matrix in the form of 1 over square root of 2 parentheses 1, 1, 1 minus 1. And its inverse, by the way, which gives you the transform again, will also be the same, because the inverse of this matrix is itself. And that transformation is a very familiar transform. It's a transform that we have for discrete Fourier transform, discrete cosine transform, discrete Hadamard transform, discrete Haar transform. All the discrete transforms in 2 by 2 will be the same as this one. And interestingly, KLT is also the same as this one, and it is quite independent from the signal, what this is, because this is always the transform that you obtain in 2 by 2. You are bound to have this transform in 2 by 2. And there is no other transform in 2 by 2. And that is, interestingly, this transform is interestingly cosine theta, sine theta, sine theta minus cosine theta for theta is equal to 45 degrees. So it's a rotation corresponding to 45 degrees. And there's a reason to that I started to explain in the previous hour. And the reason is, according to the scatter plot of x1 and x2, if x1 and x2 have close correlation, when one is large, the other one is also large. So it scatters along this 45 degrees. The data samples that you will observe will be like this. So when x1 is large, x2 is also large. When x1 is negatively large, x2 is also negatively large, like this. So the optimal transform would correspond to a rotation by 45 degrees for the best representation, like this. So now your new basis vectors are 45 degrees rotated, as opposed to the original basis vectors, which are 1, 0, and 0, 1. So 2 by 2 is an interesting case. It always gives you 45 degrees of rotation. And the question that you will encounter will be to show that it is 45 degrees rotation from another perspective of optimizing the angle, finding the optimum angle. I will ask you the question, formulate you the question, and when you see that question, you will understand what I'm talking about. And you will take the derivative with respect to the angle, and when you take the derivative, the error expression term that you will have will require that theta is equal to 45 degrees or 135 degrees. So both of them are possible. Okay, so this was the Cardinal-Loewe transform. I think we are already a little bit late. This had been a long lecture, but we can now give a break. We have to free our minds. We have to digest what we have seen. It's an important and a relatively large concept, so we need to digest it. It is 10:36 right now, so after the break, we will meet again at 11 o'clock at the same place. So until then, I will stop the meeting and give a pause to that. If you may have any questions, you can ask after the break. So see you at 11 o'clock.
See you.